You ever wonder how we can actually predict the future? With just data? Well, today we're going to pull back the curtain on a really fundamental tool for doing just that, linear regression. Now, it sounds super technical, I know, but trust me, it's a surprisingly simple idea that can predict everything from house prices to stock trends. Let's dive in.
All right, let's ground this in reality. How in the world would you predict the price of a house? I mean, there's so many factors, right? The neighborhood, the number of rooms, the year it was built. It can feel completely overwhelming. But what if there was a simple mathematical way to find a pattern in all that data to do the heavy lifting for us?
So that brings us right to our first section, predicting the price. To really get how linear regression works, we're going to build a model from the ground up, starting with just one single factor.
To keep things simple at first, let's just ignore everything else, the location, the style, the fancy backyard, and let's focus on just one thing that we know is a huge deal: the size of the house in square feet.
The tool we're going to use to do this is this simple but seriously powerful equation: y equals wx plus b. This little formula is basically the engine for our whole prediction, and it's the heart of what's called simple linear regression.
Now, this might be giving you some flashbacks to high school math class, but stick with me. Each letter here plays a really critical role. So let's break down exactly what each part of this simple equation actually does.
First up is W, which stands for weight. Think of the weight as how much something matters. For our housing example, the weight is $125. This means for every single additional square foot of space, our model predicts the price is going to go up by exactly $125.
Next is B, and that's for bias. You can think of this as the model's starting point, the base price. It's the value our line starts from before we even consider the size. In our case, even a house with 0 square feet, which, is impossible, but it helps the math work, would have a base value of $50,000.
Okay, so here are all the pieces of our puzzle. But this brings up a huge question. Where did these numbers, 125 and 50,000, even come from? We didn't just guess. In machine learning, we train a model by showing it a massive data set of existing houses with their known sizes and sale prices. The computer then adjusts the weight and the bias over and over until it finds the values that best fit that real-world data. So the numbers you see here, they're the result of all that training. And with all this in place, we're ready to make a prediction. Now for the fun part. Let's actually do it. First, we take our formula and just plug in the numbers we have: 125 for the weight and 1,200 for the size. That multiplication gives us $150,000. But wait, we're not done. We then have to add our bias, our starting point, of $50,000.
And that gives us our final answer, $200,000. So, based on its size and its size alone, our simple model predicts this house will cost $200,000. Pretty simple, right?
But let's ask the obvious question here. Is the price of a house really only about its size? I mean, of course not. The real world is always way more complicated. What about the number of bedrooms? Or how old the house is? And that's exactly where we're going next. In this section, we're going to see how to make our model smarter by adding more of these real-world factors. We're moving from a simple model to a much more powerful one.
So on top of size, we're now going to add in the number of bedrooms and the age of the house. This little upgrade takes us from simple linear regression to something called multiple linear regression. It just means we're using more factors.
Okay, so with more factors to consider, our model's parameters have changed after being retrained on new data. The base price, our bias, is now lower, down at $30,000. The weight for size has also dropped a little to $120. And, crucially, we have these new weights. Each bedroom adds $10,000 to the price. And get this, the age has a negative weight. For every year older the house is, its value actually decreases by $1,000.
So now we have our new, more sophisticated model. Let's put it to the test with that same house and see what happens. Let's run the numbers for that same house again. 1,200 square feet, 3 bedrooms, and it's 5 years old. Our new formula starts with the new base price, adds the value from the size, adds the value from the bedrooms, and then, this is the new part, it subtracts the value lost because of its age. When we plug all of that in, we get a whole new set of calculations. And our new predicted price is $199,000. A little different from our first attempt, isn't it? This comparison really shows the power of adding more data. Our simple model gave us a flat $200,000, but the upgraded model, the one that accounts for things like bedrooms and age, it gives us a more nuanced and honestly probably more accurate prediction of $199,000. So, let's just pull back for a moment and really look at the big picture. What does all of this actually mean?
You know, the fundamental takeaway here isn't just about the math. It's about how we approach the problem. We took something really complex, predicting a house price, and we broke it down into simple, small pieces. As Shilpa Thoda, the author of our source material, points out, this method of starting simple and then adding complexity is really the key to solving so many problems in machine learning.
And that leaves us with a pretty provocative question. We just predicted the price of a house, but what else could we predict if we had the right data? The weather? Stock prices? The success of a movie? The possibilities are, well, they're truly endless.